Hey guys, so today we're going to go over the unit circle, and the unit circle is just an extrapolation of what we've been going over so far with trigonometry and trigonometric ratios. And actually, if you look back to this GIF that I used, and that is GIF, not GIF for the uneducated, you'll actually notice that up here at the top it says the unit circle, and I never mentioned that before. But it's worth mentioning now since we're talking about the unit circle. Why is it called the unit circle? It's called the unit circle because it's a circle with its central point on 0, 0. You can see right here. And what I want you to notice is that the hypotenuse, that's not thick enough. Wow, that's too thick. All right. Whatever. The hypotenuse here is always 1. Okay, see how that number's 1 right there? Well, watch what happens when I play it. Notice that sine is changing, cosine is changing, but the hypotenuse is always 1, okay? So we use the unit circle to give us reference triangles for different kinds of degrees, okay? And if you'll recall from what was that, 2 weeks ago? This is Climate 74, 75, 76, 77, 78, 79, 80, it's getting closer and closer to the top. I'm going to stop at around 90 degrees, best I can. Perfect. Okay, so it's at 90 degrees now, and you'll notice the hypotenuse is 1, sine is 1, cosine is 0. And what I told you guys 2 weeks ago is that sine is the same thing if we're looking at this triangle that's being made, okay? Here, let's go back here. If we're looking at this triangle right here, sine is my y component of the triangle, or you could also think as the height of this triangle, and cosine is the x component of this triangle, or in other words, it's the base, okay? And so when we are at 90 degrees, the hypotenuse is the same thing as the y component, or the height, which is 1. And there is no horizontal component, there is no x value, no spreading out, so cosine is 0, okay? So coming from this, there are basically, you need to be able to derive a set of values for the unit circle, okay? And notice here cosine's negative at this point, okay? We'll talk about that a little more in just a minute here. So you'll notice here that for your notes today, I'm using the key instead of the blank version. And that's because I don't think it's worth our time for me to be writing in all the values in this table. That's very time consuming, and what I really want to focus on is not okay. So here's the deal, okay? You're all going to be taking pre-calc or trig next year, I think, unless you are blessed and you took probability and statistics and chose the righteous path. But if you chose the other path of either pre-calc or trig, guess what? You get to memorize this table next year, okay? You're going to have a test on it in this class next week, but obviously since you're at home, you have some certain advantages, right, in terms of your being able to use notes and things like that. But next year, you get to partake in the time-honored tradition of torturing students by making them memorize all of this. And I had to do this when I was in high school, and you get to do it now. And one thing I'm certainly not going to do is justify that to you. Okay? Sorry, but not sorry. So I want to talk about where all these values come from, how you get these values, because I will tell you, like, I can't remember this table, you know? This table's really hard. There's a lot of stuff, you know? And if you look at the Chapter 12 review, look at all these values to memorize. You have to. When I was in high school, we took a test where you had to fill out this whole table right here, And we took a test where you had to fill this out right here with all of these values, and we had to have them all memorized. It was like, you had like 20 minutes to do it. Not allowed to use your time for math, okay? But if you just memorize things right now, next year you're going to forget, right? Like, who the heck is going to remember root 3 over 2 comma negative 1/2? You're not going to remember these coordinates, right? You're not going to remember these coordinates. So what I want to try and do is, instead of spending time writing all these values in and calculating them, I want to try and give you some foundational understanding of where these values come from and why they make sense, okay? So that's our goal today. So I'm not going to do a whole lot of writing, just going to be a lot of talking and me pointing at things, and I'll draw some little diagrams to help illustrate things. So going back to the unit circle, first thing I think the most important thing to remember is that the hypotenuse is always 1, okay? So if you go back, if you think about what we learned, and again, this is too big. If you think about what we learned about 2 weeks ago, what you guys practiced, you learned about SOHCAHTOA and how sine, that's still too big. Okay, going back. How sine, can't there be like an in between? Anyway, sine of theta is equal to opposite over hypotenuse, and we talked about cosine of theta being equal to adjacent over hypotenuse, and tangent of theta is equal to opposite over adjacent. Well, let's think about these trigonometric ratios with reference to the unit circle. Well, what do we know? We know that our hypotenuse is 1. So that means in all cases always, h equals 1 when we're talking about the unit circle. Okay? If we're doing the unit circle, h is 1. So that means that these formulas are now kind of different, right? Sine of theta isn't equal to O over h because h is 1. And if you divide by 1, that doesn't change anything. So this is now just sine of theta equals O. And cosine of theta is equal to a over h. And h is equal to 1, so we're just dividing by 1. So now cosine of theta is just equal to a, because the hypotenuse is 1, because this is the unit circle. And I didn't tell you guys something before, okay? That's really important. Tangent of theta actually has a different definition besides opposite over adjacent. This is really important for, I know it's really important for calculus. I don't know if it's actually important for next year, but let's get you ready for calculus here, right? Tangent of theta is actually equal to sine of theta divided by cosine of theta. So sine and cosine are their own unique trigonometric functions, but tangent is actually derivative. It doesn't come from itself, it comes from sine and cosine. And I'll just tell you now that you're going to have math involving this formula right here in your future math life, okay? It is very important, I would say, that you memorize sooner rather than later that tangent is equal to sine over cosine, okay? And that's not as bad as you think, because I wish I had a little more room for this. Let's see. Tangent equals sine over cosine, and I'll add in my thetas. Okay, well, what is, for the unit circle, what is sine of theta equal to? Sine of theta is equal to O, right? And cosine of theta is equal to, that's not too ugly. Cosine of theta is equal to A. So doesn't that mean if sine of theta is O and cosine of theta is A, then isn't this just O over A? Tangent of theta is over A. Hey, what's our tangent formula? Tangent of theta is over A. That's where this comes from, okay? Even if the h's were here, if the h's aren't 1, it doesn't matter. You know, if you do the division with the complex fractions, the h's cancel, right? Because if I do O over H divided by A over H, that becomes O over H times H over A, and the h's cancel, so it's just O over A. Check it out. So it doesn't even matter if the h's being 1 here is irrelevant to tangent being equal to sine over cosine, okay? That's has nothing to do with the unit circle, okay? That's just a fact. Tangent is equal to sine over cosine. But I wanted to show you that this tangent of theta equals sine over cosine, O over A, we've actually been using that this whole time. We just didn't talk about it before now, okay? So that's one thing to consider. Here's another thing to consider. When I say O and A, what am I talking about? Well, here, let's back this up to like here. I'll get it to like a nice number. That's a lie. I won't get it to a nice number. That's not too bad. Like, okay, 0.7501. I'm just gonna call it 0.75. Okay. And here's what I want you to think about. If I am, I'll erase a couple things. I'm gonna erase some stuff. I need to talk about that relationship anymore. Okay. Okay. So if I'm looking at this right here, what's my reference angle, right? When I say sine and cosine of theta, we need a theta. We need an angle to be opposite from or adjacent to. What is that angle? It's this angle right here. Okay, this is our reference angle right here. So what's O? This is O. And what's A? This is A. So what does that mean? Well, if this is O, that's our y component. So remember I told you, sine of theta, that's O, that's also our y component. So sine of theta is our y component in the unit circle. And cosine of theta, that's our adjacent, which is the x component, or the base of this triangle. So cosine of theta is equal to x. Okay, I'm gonna give that a second to kind of sit with you. I know this is this is confusing information to go through. It's really a good idea, I think, to watch this lecture multiple times and pause, take notes and make sure you really understand what I'm talking about, okay? And once you understand that from this angle, this is O, which is the y component, and this is A, which is the x component, you realize that it actually doesn't matter where we are on the triangle. Watch what happens as it keeps going. Ooh, and by it keeps going, I'm just gonna force it over here. Okay, well here's my unit. Here's my triangle right here. Right, it still has a hypotenuse of 1. And notice, right now, when we talk about the angle of consideration here, I know it's labeling it right here, but really it's this angle right here. This is the angle we care about, okay? And so opposite of that angle, here's O, which is again our y component, and next to it is A, which is again our x component. So the idea of Sine being the y component and cosine being the x component is not restricted to this space up here. Okay, unfortunately this ends early, but if you have a triangle down here, like this, okay, if I have this triangle right here, this is now my, let me erase some stuff so it doesn't get too cluttered. This is now my reference angle, and this is O, which is, again, this is the y component, the height of the triangle, and this is A, this is adjacent, which is, again, the x component of the triangle. And if I have a triangle out here, same deal, right? Here's my angle of consideration. Across from it, that's my O, and that's the y component of the triangle. And over here is adjacent, and that's the x component of the triangle. So sine and cosine in the unit circle will always give you the x and y components of your triangle, okay? That is what this chart is about right here. Oh my gosh. That is what this chart is about right here, okay? So let's go through some of these values right here and try to make sense of them. First, we already talked, this is what I just got done explaining this to you. I said sine of theta is y over 1, right? Because y is the y component right here. And it's 1 because the hypotenuse is 1, which is y. So sine of theta gives you the y, which is the height right here of the triangle, right here. And then I said cosine of theta is the x component divided by 1 because the hypotenuse of 1, that's equal to x. So here's my x component. And I said tangent of theta is just sine over cosine. Sine is the y component, cosine is the x component, so it's y over x, which is the same thing as O over A, okay? So for the unit circle, the y component is always going to be the O, and the x component is always going to be the A, okay? And since this, I don't have my clipping tool open. I want to write on this, I think. Okay, and since this triangle is made from you going out in the radius to some point on the circle's circumference and then going straight down, okay, this point right here can be written as a combination of the x component and the y component, right? Because the x component is how far over we go on the x-axis, and the y component is how far up we go on the y-axis. So that means the coordinates for this point are cosine of theta, comma, sine of theta. Remember, because we write points as x, comma, y. So cosine is x, sine is y. So this is saying the same thing we just talked about in a different way. This unit circle right here then, okay, notice there are all these points going around here. These are points just like this one right here. Okay, same points, but they're going all the way around. And so the idea is that these coordinates, like root 2 over 2 comma root 2 over 2, that is the x and y. This is, well, it's two things. One, it's the coordinates of this point, okay? But that the coordinates of that point are also the coordinates of that point. Let me erase a bunch of stuff. The coordinates of this point are also, wow, that's so horrible. Let's make it a little thicker. Okay. Okay, it's still terrible. We're just gonna roll with it. Okay. The coordinates of this point our root 2 over 2 comma root 2 over 2, that's also the x and y coordinates. So the length of this base of this triangle is root 2 over 2, and the height of this triangle is root 2 over 2. So these points are telling us two things. Or these coordinates, those coordinates are telling us two things. One, they're telling us where this point is in space, and they're telling us the height and base of a triangle that has its point at these coordinates. Okay, so these coordinates are telling us the dimensions of the triangle also. So where do we get these coordinates from? Well, let's start out with some easy ones. Okay, let's start out with okay, so there are values that you need. The values that you need to know go in 15s. Okay, so you notice like every 15, well, not every 15, but 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330. I don't know why I read them all off. I was just kind of going with it. I was on a roll. Couldn't stop myself. And the good thing is, I know this is probably overwhelming for you to look at, but all you need to know is this first quadrant. Okay? If you can understand, I was really hoping you would stay. I can't get you to go away when I want you to go away. I can't get you to show up when I want you to show up. You're worthless. Okay. So, all you have to know really is 0, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Okay? And I'm not going to explain entirely why just yet, but I want you to know that this isn't quite as ridiculous as it seems. Okay? It's really just knowing about, if you can remember, and really, these ones are easy. The 0 and the 90 are very easy. So it's really just about these three, 30, 45, and 60. Okay? I'm going to help them all make sense to you, is my goal. So, first, let's talk about this. The first column here, radians, this is very easy. Okay? We already talked about, I really hate that thing. We already talked about converting from degrees to radians, right? What do? You take your degrees and you multiply. I see that's too thick for this. You multiply by pi over 180, right? So these radians are just the result of that, right? If I do like obviously 0 times this is 0, but if I do like 30 times pi over 180. 30 over 180 reduces to 1/6, so that's why you get pi over 6. Okay, so that's just that same thing is happening all the way down here. I'm not going to go through and do it because it's just the same math over and over again. It's not very interesting. We went over it already. So we talked about that. Now let's talk about one row of these values and where these values are coming from. Okay. Personally, by the way, you'll notice this circle lists the degrees and it lists the radians. Okay, so 45 degrees is the same thing as pi over 4, 60 degrees is the same thing as pi over 3, 90 degrees is the same thing as pi over 2, 120 is the same thing as 2 pi over 3, and so on and so forth. I strongly recommend, until you really go in more in depth with this next year in pre-calc or trig, that you convert everything to degrees, okay? Because the radian measurements don't mean a lot to you instinctively. You've been working with degrees for a long time, but radians are still new to you. So my recommendation is try and work in degrees as much as possible. I will tell you right now that on your test this Friday, everything is, or not everything, I don't know if it's everything, but lots of stuff is done in radians. And my advice to you, instead of struggling with the radians, is to just take a minute and convert all of them to degrees. And then once you know the degrees, that's what I'm going to do on this lecture. I'm going to convert everything to degrees whenever I can, because that's what I'm comfortable with. I don't work in radians outside of when I have to lecture to you guys. Degrees just make more sense to me instinctively. It's what I work with all the time. So I recommend you follow suit with me and stay away from the radians unless you have to use them until next year when you use them a lot. Okay? If you want to get used to it, it's fine. But, you know, you guys have enough to worry about it as it is, right? Okay, so let's do this first row right here. And to do this first row, so it's at 0 degrees. Let's go back to our unit circle, okay? Right at the start. So I said, here's 0 degrees. At 0 degrees, there's no height to this, right? So there's no height, then sine of theta is 0. And cosine is 1. Right? The x component is the entire length of this 0 degrees line. That is why sine of 0 is 0. Okay? Don't even worry about the over 2. Okay, don't forget about that. It's not useful. What matters is that sine of theta is 0. Sine of theta is 0 because there's no height component. Everything is the length. Everything's in the x component, which is why cosine of theta is 1. And remember I told you tangent of theta is the same thing as sine over cosine looks awful. I said sine over cosine, that's like saying y, wow, okay, that didn't happen. Y over x. So what's y? Y is 0. What's x? X is 1. So tangent is just 0 divided by 1, which is 0. Which means our point is, remember this is x, y, our x component is 1, our y component is 0. That's actually not that bad, is it? That's actually pretty easy if you understand everything I've told you so far about sine and cosine. If you're totally lost right now, like if I'm talking about this and you're saying, I don't understand what's going on, I really feel you should go back to the start of the lecture and watch it again, okay? It's not going to make any more sense if you don't get it right now, okay? Let's start talking about the 30 degree, okay? So first, what I want you to think about is, don't do this. Okay. Let's see if I can get this to land on 30 degrees. Perfect. Okay, so here's 30 degrees. And so if this is 30 degrees, between 0 and 90, what do I have left? Actually, you know what? I'm going to come back to this. I think this will make more sense contextually if I talk about something else first. So sorry to start this. I'm going to leave this right here. It's perfect. Okay? Yeah, I'll still talk about 30 degrees. So 30 degrees, there's the y component, the x component. Okay? And honestly, for the purposes of this class right now, okay, just type it into Desmos. Which one's my web browser? Oh, this one is, duh. I have to, okay. So, I already have these typed, but let me erase these, okay. So my angle is 30 degrees, so what's sine of 30? Sine of 30 is 0.5, which, by the way, you should write as 1/2. What's cosine of 30? Some crap. Like, what is that? Who even knows? We're going to find out in a second, okay? But what's more is sine 30 is 0.5, okay? That's very easy to write down. So here's my 30 degrees. Sine of 30 degrees is 1/2, okay? How can we figure out cosine? Okay, in our calculator, it was 0.866. Okay, and this says √3/2. How do we get that? Well, one way you can guess and check it. Okay, it's not a bad idea. We're learning this and getting comfortable. Whoa! If you type in square root of 3/2, notice how square root of 3/2 gives me the exact same decimal. Okay, so typing in radicals can be one way to check what its actual value is to see what angle we're talking about and whether you have your, like, you can guess around to figure it out. You're like, oh, is it square root of 2 or square root of 3? I'm not saying you should do that, but I'm saying if you're totally up a creek and you don't know what to do, this is a good way to verify your answer. Like if I were taking a test, for example, a big like essay, like I don't know, like an SAT kind of test, and they had this stuff on it, you bet if they said what's cosine of 30, I would start popping in these values to make sure I can get the right decimal value that matches in my calculator, you know? Like I would type in cosine of 30 and their answer would be √3/2 or something like that. So I'd start typing the different answers to see if I get the same thing at some point, if that makes sense. So it's a good, always checking radicals through your calculator is a really good idea. Be smart about it, you know? You have calculators, you can use them. Okay, so how do I get this square root of 3/2? Okay, well, let's take a little, let's make a little triangle. Oh, this is not going well. Okay, there we go. So here's my, let's use black. Okay, so here's my triangle. And this is 30 degrees. And we know the hypotenuse is 1. That's a given because it's the unit circle. And we just found out that sine of 30 is 0.5. So this measure right here is 1/2. And what we're trying to figure out is what's cosine of 30? What's this x component? Well, one way you can do this is you can Pythagorean Theorem it, right? So if I Pythagorean Theorem this, I can say x squared. Can I get more room on this? Ugh, it's a little restrictive. Why did it pull down that way? Why should it pull the other way? Whatever. X squared plus y squared is equal to the hypotenuse squared. And we don't know what x squared is, so we'll leave it as x squared. But what's y? Y is 1/2. So this is 1/2 squared, which is equal to the hypotenuse squared. So that's 1 squared, which is 1, right? So now if I do a little bit of math here, I have x squared equals x squared plus 1/4 equals 1. Okay? And cool. 34 minutes in. Now I'm going to subtract 1/4 from both sides, right? And so now what I have left, I'm going to create a little arrow up here. I have x squared equals, what's 1 minus 1/4? That's 3/4. My last step, I need to take the square root of both sides. This little dot's so hard to see, so small, I can't even tell where it is sometimes. Can you guys see that? Ooh, okay, I can hardly see it. And if I do that, well, now I have x equals, and the square root of 3 is obviously just the square root of 3, right? We can't simplify that, but what's the square root of 4? That's 2. So I get √3/2. Wait, x equals root 3 over 2. Doesn't that sound familiar to you people? It sounds familiar to me. Cosine was root 3 over 2. Okay? That's the same thing we got for root 3 over 2 for cosine of 30. So by using the Pythagorean theorem, I just got the x component of this triangle, which is root 3 over 2. And I think being able to derive that is a lot better than memorizing this big table. Okay? And believe it or not, we're almost done. I know it seems like there's a lot more to go with this table. Okay, we're not almost done with the lecture. We're almost done with the table, okay? And here's why. Okay, I had 30 degrees, just to review. Sine of theta was a half, and I did that just by punching it in the calculator. Cosine of theta is root 3 over 2. I did that by the Pythagorean theorem. Tangent of theta is y over x, right? So I do 1/2 divided by root 3 over 2, and that ends up being root 3 over 3. So notice, what do I really have to know here? The only thing I really have to know is I have to know how to punch sine 30 and cosine 30 into a calculator to find one of the measurements in an easily digestible form. And then I have to know the Pythagorean theorem, and that gives me the cosine. And then if you know what I told you before, that tangent is equal to sine divided by cosine, you can derive tangent. So you don't have to memorize any of this table, right? Nothing in this line has to be memorized. Again, I don't have this memorized. I'm doing this all as I go, just like you're seeing me. If you told me to take a test on this, and I couldn't use a paper or pencil, I just had to fill it in from memory, like you guys are gonna have to next year, I couldn't pass it without studying. Like if you asked me to do it right now, I couldn't do it. Who's gonna remember this? No one can remember this stuff. What's important is to be able to derive it. So I'm trying to teach you how to derive it right now so you can remember it for more than this quarter, okay? I'm going to skip 45 and talk about 60 degrees, okay? Let's go back to our unit circle, okay? And what I was trying to show you before, and this is when I said, I think I'll come back to this later, okay? This is 30 degrees, okay? And remember, this whole quadrant, it's too thin. This whole quadrant is 90 degrees. So when this is 30, right here, 90 minus 30 is what? It's 60 degrees. Okay? Hang with me here. Well, what about when we have our triangle is 60 degrees? Okay, I want you to check this out, okay? Right now we're at 30 degrees. So we know sine of 30 is 0.5, right? And cosine of 30 is, I'm just going to use 0.86. I know it's root 3 over 2, but I want it to match this so I can make a point to you guys. 0.866, we'll say. Okay, I'm going to let this go a little while longer. It's going up, going up. Rolling, rolling, rolling. Keep those somethings rolling. I don't actually know the song. It was a commercial back in the day for a car, I think. Kind of thing you see as a kid and you remember it, but you actually don't know what it was about because, kids don't know what's going on. Okay, I'm at 60 degrees. So now, if I'm at 60 degrees now, what does that mean? Well, no, I actually didn't want to erase that. Come back. Come back to me. Okay, so if this is 60 now, 60 degrees. If this is 90, doesn't that mean this part is 30 degrees? Isn't that flipped from how it was before? If it was 30 and 60 before, and now it's 60 and 30, Well, what do we notice about cosine and sine? Cosine is 0.5. Sine is 0.8633. So now sine of 60 is 0.866. And cosine of 60 is 0.5. Notice how these values are flipped. Pretty cool, huh? So it's even fewer things that you have to memorize. Let's go to our, it's hard to see on this table. Let's look right here. So now let's look at 30 degrees. What's the 30 degrees? It's, oh, come on. All I want to do is emphasize something. Can't you let me do that? Can't you let me do it? No, you're not going to let me do it. Okay. So it's root 3 over 2, 1/2 for 30. What's 60? 1/2 root 3 over 2. Notice how I actually just tried to point at the script with my fingers. Notice how the x and y's are just swapped. Okay? So 30 and 60 are opposites. That's not too bad, is it? 30 and 60 are opposites. So in other words, once you know 30 is root 3 over 2, comma 1/2, you actually know 60. It's 1/2 root 3 over 2. Okay? And 90 is really easy, right? It's 0, 1. Why? Because when we're straight up and down, there's no x component, and the y component is 1, which is the same as the hypotenuse. So 90... Okay. Nope. Okay, it's not gonna... 90 and 0 are opposites, right? When we had 0, the x component was 1 and the y component was 0. When we're at 90, the x component is 0 and the y component is 1, because the line is straight up and down instead of being completely sideways. So in my opinion at least, these, the 90 degrees and the 0 degrees are intuitive. Meaning, once you understand why these things are happening, I don't think you ever have to think about that ever again. Okay? What's that leave us with? We got one more. Can you look at one more and we're done with this whole circle? It's true. Okay? One more, and that's 45 degrees. So how do we figure out 45 degrees? Well, let's do another Pythagorean theorem. I know. That's what you're thinking, right? You thought, in the middle of this pandemic, I am just not using the Pythagorean theorem enough. Is it just because this eraser not good at noticing where the lines are? Like, I'm going over you. Look at this. Look, come on, how are you going through all that? Really? What is this sniper precision? Okay, let's do another triangle. That looks like that's very 45 degrees in my opinion. Okay, so this is 45 degrees. And my hypotenuse is 1. And here's the thing. 45 degrees, at 45 degrees, we're halfway to 90. At 45 degrees, the x component and y component are the same. Okay, notice sine 0.70711, cosine 0.70711. Okay, when you're halfway there, like when we were the closer we get to 90 degrees, the bigger the y component becomes, and the smaller the x component becomes. And the closer to 0 we get, the smaller the y component becomes, and the bigger the x component becomes, because the x component is going toward the cosine, the x component is going towards 1, and the y component sine is going towards 0. Okay? So as y is getting bigger and x is getting smaller, right, there has to be a point at which they're equal, and that point is 45 degrees. So here we are, they're exactly equal. So what does that mean? For our Pythagorean theorem, that means this is x and this is y, but also x equals y. So instead of saying y, I could replace this with x if I wanted to. Let's do the Pythagorean theorem. X squared plus y squared equals h squared, right? The hypotenuse squared. Hypotenuse is 1. And of course 1 squared is 1, so we'll leave it like that. And I said x and y are the same. So instead of for y, let's put an x. So I have x squared plus x squared. What's x squared plus x squared? It's 2x squared equals 1. Now I can divide both sides by 2. I'm well on my way to solving for x. That was a pretty good division line. By the way, a lot of you guys have gone quiet over the last 2 weeks. I hope you guys are all doing okay. You know, once we took a little, once we started distance learning, a lot of you guys were sending messages, you know, checking up on me or telling me how you're doing and all that stuff. But ever since they announced the schools are done for the year, you guys have been very quiet. So I'm starting to get worried about you guys. Hope you're all doing okay. Okay, so I take the square root of both sides. Let's move that up here. So that means x is equal to the square root of 1/2. What's that? Well, the square root of 1 is 1. So this is 1 over the square root of 2. Remember, we're not allowed to have the square root of 2 in the denominator. So, or any radicals in the denominator. So to multiply this by root 2 over root 2, which gives us root 2 over root 2 times root 2 is 2. So that means, let's get some blue going on here. This is root 2 over 2. And x and y are the same. So this is also root 2 over 2. So if I go back to this, right here, notice for 45 degrees, what do I have? Root 2 over 2. Root 2 over 2 for sine and cosine. Boom, we just did it. Did I have to remember anything? No. Nothing. Well, the Pythagorean theorem, but man, if you don't know the Pythagorean theorem by now, whew, that's not good. And then tangent, what's tangent? It's sine divided by cosine. Well, sine is root 2 over 2, and cosine is root 2 over 2, so it's anything divided by itself. It's 1. So the tangent is just 1. Okay? And if you look at here at 45 degrees, you'll notice, okay. You'll notice this is root 2 over 2, root 2 over 2, just like we calculated for 45 degrees. Why can't I just do what I want? Okay, and we're basically done. Okay, this is what you have to remember. Okay, you have to remember 0, 30, 45, 60, and 90. What are these other numbers down here? What's the rest of this over here? It's nothing. It's nothing at all, because it's actually all very easy to understand. Okay. I didn't think about how to draw that for you. Let me think about that. How do I want to portray that for you guys? Yeah, I think we'll do it right here. Okay. I'll do it here. So here's what I want you to think about. Okay. Here's our triangle. Let's say instead that the triangle's going right here. Oh, that was pretty good diagonal, isn't it? Yeah, I'm pretty impressed with that. Okay. And this is 45 degrees. Okay. Well, this is root 2 over 2, right? And this is root 2 over 2. Except there's something extra. Look at my x component. It's going back on the x-axis. So I make it negative. That's it. Let's take a look at our unit circle over here. Let's look right here. Okay. At 135 degrees. What do I have? Negative root 2 over 2, root 2 over 2. Just like I had over here. Negative root 2 over 2, root 2 over 2. So note, what I want you to notice here is that this circle is actually repeated 4 times. We've got this first quadrant here. Okay? These other 3 quadrants repeat all the values except the signs flip. Okay? So you'll notice here, like, let me zoom this out a little bit. Okay. I think maybe best if I do it this way. When I am at 60 degrees, okay, it's at 1/2 root 3 over 2. Well, what about when I'm at 300 degrees? Well, at 300 degrees, look what kind of triangle I make. And notice here, this is 1/2 root 3 over 2. This x component is positive. So this is 1/2. This is 1/2. My y component, though, is going down now. So instead of being positive root 3 over 2, it's negative root 3 over 2. Okay? That's it. This whole thing is repetition. Okay? So if you have, if you're looking at this triangle right here, okay, that's a repeat of this triangle, which is also a repeat of this triangle, which is also a repeat of this triangle. So notice these values all match up, right? Root 3 over 2, 1/2. Negative root 3 over 2, 1/2. Negative root 3 over 2, negative 1/2. Negative root 3 over 2, positive. Root 3 over 2, negative 1/2. So notice these values, this root 3 over 2 gets repeated 4 times. But when the x component of the triangle is going back into the negatives, the negative part of the x-axis, the coordinate is negative. And when the y component is going down on the y-axis, below the y-axis on these two, notice that my y component flips to negative. That's all there is to it. So really you just have to know this quadrant right here, and then flip signs. So when we started this, you probably thought, this is horrible. How can I remember all this? And you probably saw this and said, this is just, why are you doing this to me? But now you should hopefully realize, it's not that bad. That's not that bad. You can derive almost all of this with logic. So you just have to not hate thinking. So hopefully you don't hate thinking too much. This down here is just talking about that, okay? So the idea is this. If you have, if you go back to geometry, there are 4 quadrants, right? This is quadrant 1. Actually, I don't want to do it right there. This is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. Somewhere, some genius said, it really would be a great idea to start in the top right corner for naming these quadrants, and let's just do it counterclockwise from that perspective. Yeah, thanks a lot. Why couldn't it be like reading? 1, 2, 3, 4. Wouldn't it be great? 1, 2, 3, 4. No. 1, 2, 3, 4. Anyway. And here's what you have to remember, okay? If you got a triangle anywhere in quadrant 1, my x component is positive, and my y component is positive. So these are both going to be positive. If I have a triangle in quadrant 2, my x component is negative. My y component is positive. If I have a triangle in quadrant 3, my x component is negative. It's going back on the x-axis. And my y component is negative. It's going down on the y-axis. And if I have a triangle in quadrant 4, the x component is positive and the y component is negative, going down the x or on the y-axis. Okay? So that's for sine and cosine. Okay? So sine and cosine, just look at the x and y components of the triangle and where they are in terms of negatives and positives. Okay? So all we have left is tangent. And tangent, in my opinion, is not any trickier. Okay? For tangent, what I want you to do, it says, remember the phrase, all students take calculus? All students take calculus? I don't like that. I'm not going to do that. Okay, here's what we're going to do instead. My way's better. Like always, right guys? Say yes, Mr. Dufresne. Okay? Make your parents think that you're losing it in your bedroom or wherever you're watching this video. Okay, so tangent, for these purposes, think of tangent as the hypotenuse. Okay? And ask yourself, if this is a line, is the slope of that line, oh, that's like too much. That's okay. Is the slope of this line positive or negative? It's positive, right? So this is a positive line. And if you have a triangle down here, and this is my hypotenuse, what's the slope of this hypotenuse? It's positive, right? It's going up and to the right. So these are quadrants where tangent is positive because the hypotenuse is a positively sloped line. And if I do them in these quadrants, quadrants 2 and 4, notice that my hypotenuse is downward slope. It's a negatively sloped line. So right here in quadrant 2, tangent is negative. And same thing in quadrant 4, tangent is negative because this is negatively sloped. Okay? Another way you can remember this, if you don't like that method, that's my method. That's one method. I like that method. It's what I usually go to. Another thing you can remember is that tangent is equal to sine over cosine. And you guys know the rules for dividing negatives and positives. Well, if I'm in quadrant 1, my sine is positive and my cosine is positive. Positive divided by positive is positive. In quadrant 2, cosine's negative, sine is positive. So what's a positive divided by a negative? It's a negative. If I have a negative, negative divided by a negative is a positive. And in quadrant 4, if I do a negative divided by a positive, that's a negative. So you can think of the hypotenuse and its slope to figure out the sine value, the positive or negativity of tangent, or you can think about how it's the result of dividing sine and cosine. Okay? I think the only thing left to talk about is just talking about, like, what do you do when you have something like... So first of all, if you have something like cosine of 11 pi over 6, I really recommend you just convert that to degrees. Okay? Don't mess with pi over 6. Or don't mess with the 11 pi over 6 right now. Keep it easy on yourself. Convert 11 pi over 6 to degrees and work with that is my advice. I didn't say this explicitly, but I should right now. Okay, we're just doing a little cleanup here at the end. We're almost done, guys. It's like ripping off a 45 to an hour Band-Aid. Like ripping it off, putting it back on, ripping it off, putting it back over on. It's just math in general, I think. Okay, so right here, if it was straight out, okay, pretend that's straight in a line, that was cosine of 0 equals 1. It was straight up, that was sine of 90 equals 1. So if it goes back, you know, hopefully you figured out that's cosine of 180 equals, that's an equals, -1, right? Because it's all on the x, and it's going back along the axis, so it's going to be -1. So what do you think? What's sine of 270 going to be? If you said -1, good job. If you didn't say -1, that's okay. But I hope you understand why it's -1, right? Because it's the same thing as sine. It's just y component. There's no x component, but it's going straight down on the y-axis instead of going straight up. Does your head hurt yet? Do you feel pained by all this? Okay, let's have one more thing. And I think for this, this one. This actually went better than I thought. Maybe you're thinking like, Mr. Frayne, you're a disaster, but I'm happy. And if I'm happy, I'm happy. I can't say you're happy, but I'm happy. Okay, so let's have something like 210 degrees. Okay, here's 210 degrees. Okay, when you're drawing these triangles, because you got to figure out like, what is 210 degrees similar to? Always go out to the point and then go back to the x-axis. Okay, don't go to the y-axis. That's not a thing. Go to the x-axis every time to make your triangle. And now to figure out what kind of angle this is, okay, just ask yourself, how many degrees away from the x-axis is it? So this is 210. What's 210 minus 180? That's 30. So this is a 30-degree angle. So that means you use the values from sine of 30. Okay? You could use 210. You know, if you want to do like sine of 210 and stuff like that, that's fine. But think about logically. Again, I don't want you to memorize this. I want you to be able to think through it. Think about it as 30 degrees, and then just flip the signs for sine and cosine, right? Because if you're doing this, we're in this quadrant, so both cosine and sine are negative. Okay. What if I have 300? Okay. Well, here's 300. And if I come back up here, how many degrees away am I from the x-axis? Well, that's at 360. So 300 to 360, this is a 60-degree angle. So that means this will have the same x and y's as, whoa. This will have the same x and y's as the 60-degree triangle. 1/2 and √3/2, and we flip the sign of the √3/2 to negative because this y component is coming down. Okay? So I think that was a better use for time than me filling this entire thing out one thing at a time. These are a great brain exercise for you guys to do to make sure you understand the quadrant ideas. We talked about this. This is just a handy table, okay? You should know that, make sure you're on eCampus. You have to be on eCampus to watch this anyway, but if you haven't already, I sent you guys a message on eCampus about changes to class expectations. Make sure you guys read that. This is the only video for this week. It covers everything. It's short, I think, okay? And next week we're going to cover the joy of graphing sine and cosine. So I hope you look forward to that, because I am. See you guys.